Hi everyone, welcome back to GridPro. In today's video, we will see how to efficiently mesh a rocket nozzle with a domain. We have created a geometry for the rocket with a nozzle in GridPro's CAD panel. The 2D curve was created by specifying the coordinates of the vertices. Then, the curve was revolved about the axis to get a complete three-dimensional axisymmetric geometry. Let's triangulate the CAD file specifying the appropriate parameters to convert it to the surface. Once triangulation is done, load it as surface in GridPro's surface panel by splitting the surfaces automatically. We can merge the surfaces where we don't want them to be split, group the surfaces in the surface group, and merge them using the merge operation. An elliptical domain can be created by using the ellipsoid feature in the Create section. We will specify the already noted parameters to create the elliptical domain around the rocket. Also, create a plane which will act as an outlet surface. Cut plane can be taken at origin normal to z-axis to visualize the geometry clearly. This way, the rocket nozzle with domain is ready for the topology generation. Now, let's start with topology building operations. We can create a 2D axisymmetric topology, which can be revolved by 360 degrees to get a complete topology for the rocket nozzle. Create simple quad topology for the nozzle. Add multiple inserts to capture the surface features. Positioning the corners near the surface helps in quick convergence of grid, saving grid smoothing time. Delete the corners sitting inside the rocket body as we are meshing only the nozzle. Next step is to extend the topology up to the far field and outlet of the domain. Copy the external corners of the rocket forebody near the domain surface. Then align them to the domain wall. This allows the corners to be positioned precisely on the domain surface. Copy the outer sheet near the nozzle to the outlet surface. This creates the basic 2D wireframe for the rocket nozzle. Select the corners around the nozzle wall and do one boundary wrap to create an O-grid. Similarly, group the corners defining the rocket forebody and base and do one boundary wrap. We can assign the corners to the respective surfaces. In the 2D topology, the corner assignments will be retained for all the similar corners in the revolve 3D topology. Check button can be used to check the assignments of the respective surfaces. Additionally, we will create two internal support surfaces to address the sharp nozzle trailing edges. These surfaces can be created in the GridPro by using the internal surface tool. For now, we will load the earlier created internal surfaces. We have added the inserts such that it will create one-to-one connected sheet representing the internal surface. Assign these sheets to the respective internal surfaces. The next step is to revolve the 2D wireframe to create a 3D topology. We can use GridPro's revolve with core option, which automatically creates core topology at the axis, such that the singularities are avoided. Let's revolve this wireframe about the center of the nozzle along the x-axis with 16 copies of the sheets. We'll use the corner group C1 as input for building the core. It's advisable to enable the Update Corner Group option. This updates the corner groups by adding the corresponding corners from the revolved topology to the existing corner groups. Click Copy to generate the complete 360-degree axisymmetric topology. Group the sheet assigned to the internal surfaces and do one internal wrap with insert for both the surfaces. The validity check shows the topology has 1520 number of blocks. The topology is valid with medium singularities near the rocket tip. We can resolve this warning by creating one boundary wrap on the sheet assigned to the rocket body and the base. Checking the validity again shows the topology has mild singularity at the rocket forebody and base intersection. This mild singularity can be addressed by either creating an internal surface similar to the nozzle base or adjusting the grid density equally on both sides of the singular edge. Now, let's adjust the densities using the length-based option. Here we need to set one reference edge, and the densities of all topology will get adjusted according to the lengths of the edges. Additionally, we can set edge densities as needed in the desired regions. Let's run the grid smoother to check the resulting grid. After loading the grid, we can see that the grid is smooth Slice can be taken to visualize the cross-sectional sheets. As we can see, the rocket nozzle body is captured precisely. The quality dialog box shows the grid has a max skew of 0.82. We can run the grid smoother for more number of sweeps to converge the grid further. Additionally, we can add the inserts and modify the densities in the specific blocks and refine the grids in desired regions according to the flow physics. We hope this video was helpful in getting an idea of efficient meshing of geometries similar to axisymmetric nozzles in GridPro. If you have questions, feel free to contact support at gridpro.com. Thanks for watching.